with chapter 13, where we started back in January.
This is where I started struggling. We were here in January?
We were.
Are you sure?
Yep.
Because it's so cold in here.
We talked about properties of solutions. We introduced quite a few different but important concentration methods, right? Discussing how to calculate concentration. Yeah. He could have bought just a 3-subject notebook. That would have helped.
But then I can do this.
All right.
Now I can flex on them all. I finally have them.
Fair. Before we started talking about concentrations, we talked about the concepts behind solutions.
No one told you to rewrite the book. But they can't get me a copy right now.
Okay. When solutions dissolve is where we started. With the topics of solvation and hydration. Okay? Solvation is going to be when solvent surrounds what? Say it again. Solvent surrounds something else. What's the other part? Solute. Okay? Solvent particles surround solute particles. Hydration specifically is when water surrounds our solute. Along with this, we talked about the concepts of about a couple of different concepts along the lines of saturation, unsaturation, supersaturated, and when a supersaturated system occurs, when we cool it, we can get this crystallization to occur. That crystallization tends to be a purification method. That results in a substance that has had its impurities removed. We also discussed in this section solubility. Solubility is typically reported as an amount of solute that can be dissolved in an amount of solvent. This type of indication is used to create a saturated solution. Right? So if we report the solubility of salt as 250 grams of salt in 100 grams of water, what we're saying is in order to create a saturated solution, you have to dissolve 250 grams of salt into 100 grams of water. That was sections 1 and 2. Section 3 discussed the idea of miscible and immiscible. When something is miscible, what does it mean? No. Try again.
I like it.
Say again? Dissolvable. Good idea. These two can be mixed, dissolved, whatever you want to say. Okay, what does immiscible mean then?
Unable to be mixed.
Unable to mix permanently or adequately.
I'm right there with you.
I can't spell.
Permanently. It works for me.
Permanently. I probably spelled it wrong. I think it's an A. Cool. Whatever. Permanently. Remember that the old adage is like dissolves like. What does that mean? No. No. Polar and polar.
It's okay.
We're just letting it happen.
Okay. I don't like that one.
What else does it mean aside from polar dissolves polar?
Non-polar.
Thank you. Dissolves.
Non-polar.
Thank you. Next up is formulas. Concentrations. Section 4. Today's question. How do you use these different formulas? I did tell you to look them up. First is mass percent. Mass percent is the mass of a component, let's say A, or the total mass, times 100%.
Is that in grams? Yeah.
Isn't anything. Just make sure it's the same thing on top and bottom.
Correct. Yes. When in doubt in chemistry, it's in grams if I say mass, yes.
Look at me like that.
I am looking at you like that. That was January. Actually, that was sophomore year,
That's why we don't know it.
chapter 4.
You know what software? It was very fun.
I don't care.
It was easier than this.
ppm and ppb. Then we had mole fraction. Then we had molarity and molality. In molality, please remember that the mass is always in kilograms on the bottom. And it is the mass of the solvent, not the whole thing. Just the solvent. I think those are it. Then we talk about Raoult's law. over mass of solvent in kilograms. You'll get a formula sheet. All right. Then we talked about colligative properties. Those colligative properties were going to be ones that depend on the concentration. So properties. Not the identity. Anybody remember some of the colligative properties that we talked about? Freezing point depression and boiling point elevation. This is the dry ice lab that we messed with, where we measured the impact of different molalities of salt, and then we compared what happened as we add different amounts of salt to the freezing point to what happened to the same molal amount of something like sugar, right? And we kind of looked at what happens if you have multiple ions dissolved in solution versus one. I'm erasing my formula. Okay. RAU. Raoult's law, which states the impact the mole fraction of the solvent times the ideal pressure of the solvent. To do with pressures. So the pressure of something would be equal to the mole fraction of that solvent present times the ideal pressure or standard pressure. Vapor pressure is what this is. And this is the standard vapor pressure. Remember, that's what the little knot means. So this would have to be something you were given, something you might have to calculate using a mole fraction, and then you were able to find the pressure of a solution, vapor pressure of a solution. What is a vapor pressure? Good, guys. That's a vapor, aka the pressure of the gas right above the liquid. And depending on the liquid, you'd have different ideal vapor pressures. All right. Yeah. Last thing in this particular chapter was colloids. All right. And you'll remember that colloidal suspensions. Well, milk is a suspension. Good. Blood is also a suspension, but not a colloid.
Lights.
Scattering of lights.
The Tyndall effect.
There you go.
That's what you're going for?
Yeah. Well, I wasn't really going for anything. People just started yelling things.
I have it in my notes.
The Tyndall effect. Right? So a colloid, which is going to be a little bit larger as far as particle size than a solution, will scatter light but does not necessarily completely obscure light, right? Whereas a suspension will completely obscure light and very likely allows little to no scattering. Yes?
Do we actually have a Van Hoff factor?
Oh, the eye?
Hold up, hold up.
Is that one what you're talking about? So I is related to, sorry. I is related to how many particles are dissolved. So in lab, what we did, for something like salt, I is 2. For something like sugar, I is 1. Because when salt dissolves, it dissolves into 2 different parts. That's why the I becomes 2. Right? So yes, we did talk about this change in freezing point. We did do some information around this. What is M in this equation? No. Molality. Lowercase m is molal. Molal. What does K stand for? Freezing point. In this case, because it has an F, freezing point depression constant. It's a constant.
Something that stays the same.
Remember that anytime we see a capital K, you probably have to get a constant or pull a constant from somewhere. We're getting there.
Wait, is that a capital K or is that a...
That is capital K, but it's the freezing point depression rate constant is what it is. You technically didn't know about rate constants until chapter 14.
So what's this good for?
This is 13?
I'm talking about the...
This?
Yeah.
So this is for the change
Okay.
in temperature
Mhm.
for a freezing point
Yeah.
is equal to the Van Hoff factor, which is the I, we just talked about that, right? Times the freezing point constant times the molality of the solution.
Okay, so the K are together.
Correct.
All right.
Yeah, that's one. Sorry.
And can you explain the I one more time?
Sure. We could do it for boiling point too, but it's the same thing.
All right.
Okay? So I is related to how many parts will it break into when it's in solution.
All right.
So if you think about NaCl, it'll break into 2 parts. What about that one? 3 parts. Okay? You would either be told what I is or be given a description of how to calculate it.
Oh, all right.
Right? Assume I, is this. Or assume this breaks apart into this many parts. What is I? Is a good question. But if I give you something like CaCl2 and I say breaks into all of its ions, how many ions are going to be present if one molecule breaks down? You should say 3. And that's the value of I. Something we did in lab. All right, moving on to chapter 14.
We make some Excel graph.
Chapter 14 involved chemical kinetics. Looking back at it is probably a lot easier than learning it at the time, but chapter 14 involved
Boo.
rates.
Boo.
Why do you hate chapter 14?
That's when the math starts getting hard.
No. So I felt like I
All right, chapter 14, section 1.
That was one of the bad ones, but it wasn't the worst.
Equilibrium was when I started. That was hating on my life.
Ice table. After the ice table.
Answer the question, what exactly is a rate of a reaction? And introduce the idea of the term chemical kinetics. That's all this section did. It was very brief. So what is chemical kinetics?
I don't know.
Yes, you do. Think about it.
Hey,
Chemistry to do with movement.
How quickly,
a reaction occurs.
meaning involving time, does a reaction happen? What is a rate?
Okay.
Change in something over time. All right. Section 2 discussed instantaneous rates. When you think of an instantaneous rate, it means the rate at a single instant. So think the radar gun. How fast is it happening at a specific instance in point in time? In our particular case, rates are going to be change in molarity over change in time. Or is that delta molarity over delta time. When we think of instantaneous rates, we can also use a graph of molarity versus time to say what exactly is the concentration at a specific time point, right? So this is how we can actually calculate an instantaneous rate. We can take a concentration value at a specific time point, and we can compare it to, say, an initial value. And if we compare it to an initial value, we've got a change in molarity over a change in time. In this case, is our change going to be negative or positive as we go to the right? Negative, right? Because the thing is disappearing. Okay. Which brings us to section 3. Rate laws. Anybody remember what the general form of a rate law is?
Is K and then a rate equals K and then it's the concentration split and then exponent and then concentration.
Okay, so there's an instantaneous, or I'm sorry, that's a rate law, right? Parts of this that we need to remember. What's this small k?
Rate constant.
A rate constant. How do we determine the rate constant for something?
K equals products over reactants.
Different k. You're not there yet.
How many K's are there?
Try again.
Too many things.
Log.
There are a couple of ways. One of them,
Okay, why is it always K though? Like there's a lot of
experimentally.
The table, 1 means
Right. K is an experimentally determined value. That's it. Okay? There is no way to determine K without some form of experimental data. All right, what about A and B?
Concentration.
Concentrations, good. X and Y, coefficients. Are A and B reactants or products?
Reactants.
Thank you. What is this guy? Rate in concentration over time. Oh, it's been a while. All right. Aside from rates, another way that we can talk about this involves reaction orders. So what information can we get from this?
First order, second.
Right, so we can do per reactant, or we can do overall order. So if we get this, what is the rate order or the reaction order with respect to A? B, overall, add together. Okay.
So we just really count 1, 2, 3.
What?
We really just counted 1, 2, 3.
Yep.
That's a lot of work to do that.
Aren't you proud that I made you do that out loud? I have my moments.
It's stressful.
Huh?
It's stressful.
Nah.
Try to do the to go 4 or 5. Too much pressure to go.
Say again?
Too much pressure to go for 4.
Reaction mechanisms. Trying to decide how to do the next part. Okay. General form of a reaction. Lower cases are going to be coefficients. Upper cases are going to be the actual compounds. Please remember that one of the ways that we can predict is using just the reaction itself. As something disappears, it gets a negative rate. If we can predict the rate at which something disappears, we can predict the rate at which they will appear. So these are my rates of disappearance that I can predict. The rate at which they appear then becomes a positive.
Is that first one saying that you multiply? Like,
Yes, that's what the dot means, yep.
Well, I normally remember this one.
I couldn't tell what it was.
So that was the first thing that we could do involving rate laws is we could predict what would happen given just the actual balanced equation. Yes.
Little numbers are coefficients, right?
Yes. So remember so lowercase letters are going to be coefficients, uppercase letters are going to be the actual species. All right. Then we come to experimental determination of a rate law using tabulated data. We're going to talk about first order, we're going to talk about second order, and we're going to talk about other orders. For now, this is section 4. Too far. Oh, actually, this is section 3, but whatever. All right. Doot, doot. We're going to do experiment number. Then we're going to do concentration of A, concentration of B, and we're going to do initial rate. right, so we have this table of data that lists different experiments that were done. What we did was we held things at different concentrations initially, and we calculated what the initial rate was as a result of those initial concentrations. Remember, when we do this, we're trying to determine a rate law, okay? If something is first order, remember that its exponent will be 1. If something is second order, its exponent will be 2. And we'll talk about what that means here in a second. And I'm going to write etc. for other, right? Because if we could get a third rate, a third law, if something went up to an exponent of 3 or 4, etc., etc. All right. So when we're trying to determine the order with respect to A, what do we have to do for B? Find where B stays the same. We want to hold B the same, and we want to monitor what happens to A when we hold B the same. Okay? So in experiments 1 and 2, B doesn't change. What happens from 2 to 1 as far as A is concerned? It goes up by 2. Since I'm going from 2 to 1, which doesn't matter, it doesn't matter what order these are done in, when I go from 2 to 1 as far as the rate, what happens? It doubles. So,
So is like the first two like the A part, and then like the second two is like the rate part? Is right there?
yes,
Okay.
yes. So you go, whatever this change is to an exponent has to equal whatever the change in the rate is. Good question.
Why does that one, why does it matter? Why does the 1 matter?
We're trying to figure out what the rate law is, remember? So our goal is to write a rate law expression that involves both of these things raised to whatever power they should be raised to, using experimental data instead of a balanced equation. Okay, so now let's look at B. We have to find 2 where A is held constant and B changes predictably. So from here to here, what happens? As we went from this experiment to this experiment, we multiplied it by 2. What happens here? Times 3?
Mister, do you want to know if you have a deck of cards?
A what?
Deck of cards.
I do. It's not complete. Make sure he knows that. It's missing cards. Thank you.
Way to go, Bert.
I meant to make that 4.
Yeah, that's gonna be a little tough.
Oops. So what happens? Thank you.
Oh, watch your gosh.
All right, so as one thing doubled, what happened to the rate? 4. I changed it. So what's the exponent? Then we write a rate law including our determined rates from the experimental data. Ring a bell? Kind of, sort of? Clear out those cobwebs on chapter 14. There's a lot of good stuff in 14. Okay, so this is one of the other ways that we could determine the rate law. We will continue tomorrow.
Can you send me over notes from before I got here?
I didn't